for coming today. So today we have a seminar from Yun-Ting Cheng, who is currently a postdoc at Caltech. So Yun-Ting got her bachelor degree from NTU Physics back in 2014,
yeah.
Right? And then after that, she moved to Caltech as a graduate student in the physics department of Caltech. And in 2021, she graduated with her PhD in physics and then started as a postdoc at Caltech in the observational cosmology group. And so today, Yun-Ting is going to tell us about cosmology and astrophysics from the extragalactic background line. Let's welcome Yun-Ting.
Yeah, thank you, Yikwan, for the introduction. So, hi everyone, I'm Yun-Ting Cheng. I'm now a postdoc at Caltech. I will work with Olivier Doré. Okay. And I'm very happy to be back here in ASIAA again, and also very happy to see everyone here in the room. Yeah, this is my first in-person talk since the pandemic, so I'm now very excited to see the real people here in my audience. Okay, so today I'll be sharing you about my recent work on cosmology and astrophysics from the extragalactic background light. Okay, so what is the extragalactic background light, or the EBL? And the EBL is basically the integrated light coming from all the sources in our universe, coming from all redshifts and across all frequencies. Okay. And here's the EBL spectrum from optical to far infrared. Okay. And here in this spectrum, okay, the shorter wavelength emission from about UV to mid-infrared, they are mostly coming from all kinds of stellar synthesis processing of universe. And at the longer wavelengths, these are mostly coming from dust that absorb some of the stellar emission and re-emit the thermal radiation in the far infrared. Okay. And in this talk, I'll mostly focus on the EBL at around near infrared part, so it's a spectrum at around 1 micron here. Okay. And as you can see, there are a lot of different measurements of the near infrared EBL here. And also, these measurements has very large scatters between each others. And this is partly because they are taken with very different kind of methods. So how can we constrain this EBL at this wavelength? Okay. So the first way to do this is to use galaxy counts. So galaxy counts means that you take your telescope, you point to a part of sky, and then you do a very deep integration and try to resolve all the galaxies you can, and you count the total amount of photons coming from all these galaxies. So this gives you a lower bound constraint of the EBL, because you cannot get the light from the sources below your detection limit. So these upper arrows here are the constraint using galaxy counts. And another way we can measure the EBL at these wavelengths is to use absolute photometry. This just simply means you measure what's the total intensity coming from the sky. So in this case, you can get the light coming from all the sources, including bright and faint galaxies. But also, this is a lot more challenging because now you have to carefully account for all the foregrounds and all the systematics. So these data points here are using the absolute photometry measurements. Okay. And one very big question in this near infrared EBL field is that if you look at the data coming from these absolute measurements, they are a few times higher than these galaxy counts. So that means in our near infrared sky, there are a lot of photons is coming from very faint or very diffuse sources. They are not being captured by even the very deep galaxy integrations. So what are these very faint and diffuse emissions? So there are a few kind of theories people proposed. So first, they could be the sources coming from the epoch of ionization. And these first stars, first galaxies, they are very faint and also very far away, so it's very hard to detect them individually. And also, there could be some lower redshift galaxies, and they are also very faint, so they are also below the detection limit for those deep integrations. And also, another possibility is called the intrahalo light. These are coming from the stars that has been tightly stripping away from their host galaxies during the galaxy merger. So these stars just floating around inside the dark matter halos, but they are not really tightly bound to the galaxies. Okay. So all these kind of lights will be living in this an EBL emission in this background light, but we cannot resolve this emission individually in the usual galaxy photometry. Okay. So I hope this gives you some idea that there are a lot of interesting science we can do with this background light without trying to resolve the individual sources. Okay. Okay. So the main question I want to address in this talk is that, okay, so how can we extract either the cosmological or the astrophysical information we want from these EBL measurements using multi-frequency imaging data? So that means we directly look at the raw image coming from the telescope. So we have a measurement of the intensity as a function of pixels or the angle on the sky. And then we usually use the multi-frequency data or the multi-bands. Because with the multiple frequency, we can better distinguish the source of the emission and also to extract more information on the property of the sources. Okay. So below I'll cover 2 of my recent works related to this topic. Okay, so let's look at the first one, the EBL tomography with cross-correlation. And here I'll introduce our work on Spherics and galaxy cross-correlation. And this work is in collaboration with Zhijing Zhang. She's now in JPL and Caltech, and I'm sure many people here know Zhijing very well. Okay, and this work has been published on FJ earlier this year. Okay, so first I'll give a brief introduction on Spherex. So Spherex is an upcoming satellite mission that will be launched in 2024, and it will be the first all-sky named for a spectral survey. So for any given line of sight on the sky, Spherex will take a spectrum from 0.75 to 5 micron. And the spectral resolution is somewhere between photometry and spectroscopy. So its resolution R is about 40 at a shorter wavelength and about 100 for the longer wavelengths. And it has, in total, have about 100 spectral channels. And you will reach the point of sensitivity at about 19.5 magnitude per spectral channel. So this is a lot more deeper than the previous all-sky survey from 2 mass at the same kind of wavelengths. And it also covers a lot more spectral channels with a lot better spectral resolutions. Okay. And here are the 3 main science goals for Spherex. So the first one is to do cosmology. So Spherex will map a bunch of galaxies on the skies on very large scales. So we can use this to trace the underlying larger structures to constrain the primordial non-Gaussianality. Okay. And the second part is to study the galaxy formation and evolution using the extragalactic background light. Okay. And the third part is to try to detect the water ice signature inside the ISM. And here I'll only focus on the second part. So studying the extragalactic background light using Spherex. Okay, so here on the left, I'm showing a model of the EBL that will be observed by Spherex. So if you see this black line on the top here, these are the total spectrum coming from all the galaxies integrated over all the redshifts. And here's a spectrum from 0.75 to 5 micron in the Spherex observing bands. So if you just look at the total spectrum here, then this is a very, very smooth function because you integrate all the emission across all redshifts. But if you want to look at the this EBL emission coming from the galaxies at different redshifts, then you can see at each redshift you will have very different features in this SED. For example, like you have a bunch of spectral lines, and also the shape of this continuum is different because of their intrinsic emission is different, and also the SED is redshifted. Okay, but all of this information is degenerate if we can only observe the spectrum here. Okay. So in this work, we are trying to see if we can detect this redshift-dependent EBL spectrum, or these color lines here, using cross-correlation. And the idea is pretty simple. So you can take the Spherex image here. So Spherex image is an intensity map. for each frequency channels. And then we can cross-correlate with the galaxy tracers at different redshifts. So when we do one of these cross-correlation, then you will only extract the EBL emission coming from the same redshift as your external tracers, because only the stuff in the same co-moving volume will have the correlations. So then you can get a point on one of these color lines here. And if we do all these different cross-correlation, then we can map out all these color lines. Okay, so that's the basic idea of this cross-correlation. Okay. And this method is also called a clustering redshift estimation, and people have been using this for other broadband photometry imaging survey. And also Yun-Ting here is an expert on this method. Yeah, he has wrote a lot of paper on this. Okay, right. Okay, so when we do this cross-correlation, we'll get this cross-power spectrum. So we look at the correlation in the Fourier space. Okay. So here's one example of this cross-power spectrum. So here I take one of the Spherics spectral channel, so it's a Spherics image at around 3 micron, and I cross-correlate with the galaxy sample also generated by Spherics at redshift 1. So we'll get a spectrum like this. So in this cross-power spectrum on the large scales, the signal is dominated by the clustering signal, and this clustering term is coming from the total EBL emission at that redshift. Okay. So the clustering amplitude here, the CL power spectrum, is proportional to some bias factor, and this DIDZ, that is the EBL emission as a function of redshift, and it's tracing the underlying matter density field here on large scales. Okay, so we can look at this clustering amplitude here to try to extract the redshift-dependent EBL information here. Okay, and on the small scales, the signal here are dominated by the Poisson noise because the galaxy tracers are the discrete sources. Okay, and this Poisson noise is also proportional to this DIDZ factor, but only on the galaxies we are cross-correlating with here. Okay, so this is just like doing the stacking on these external tracers. Okay. And according to our forecast here in this example, we can get a pretty high signal-to-noise ratio on these measurements. So on a clustering scale, if we average the signal coming from all these L modes, then we can get an SNR for about 25. So this is a pretty good measurement on this clustering amplitude. And for the Poisson noise, we can get above 1,000 of SNR. And this is because SPHEREx is an all-sky survey, so we have a lot of small-scale mode that we can measure. Okay. Yeah.
That's a very nice question. You consider crossbar spectrum. Why do you have short noise?
So the question is, why do you have short noise in the crossbar spectrum? Okay.
Right.
And so, because you can think that even if there are two different tracers, but the EBL emission are also coming from the galaxies.
Right.
So you are just looking, it's just like you pick out a subset of galaxies in the EBL. Mm-hmm. So you still have the short noise coming from those sources.
Great. I think I have another question. Do you expect that the short noise becomes such a very beautiful Poisson noise, or don't you expect short noise can be sub-Poisson?
You mean on a very small scale?
Yeah, it goes to the Poisson very well. So yeah, I mean, it looks very well behaving. Do you expect that?
Yeah, I think on the very small scale at maybe around the PSF size or the typical halo size, then you might have some signal suppression because of the signal is kind of smoothing out. Yeah.
Right. So yeah, this result looks much better behaving than expected.
Yeah, I think we didn't consider that in our forecast. So yeah, that's a good question.
This simulation.
This is just a modeling.
Okay.
Right.
So I was just wondering, for redshift 1, what kind of galaxy sample are you considering here?
I'm not quite sure. Oh, I think this one is the SPHEREx sample. So SPHEREx is a low resolution spectroscopy. So it's more like a spectroscopic galaxy samples.
I see. Okay. But the reason I ask is that usually redshift 1 is the regime where we have the smallest galaxy sample, where the statistics is the poorest. So it's good to see that you get good signal to those.
Yeah, I think so. A redshift 1 SPHEREx can actually get a pretty good catalog. And also, the one advantage of SPHEREx is that it'll cover the whole all sky, so we can beat down a lot of sample variance.
Yes.
Right. Okay. And in the paper, we do consider this cross-correlation with a few different galaxy samples. So some of them are spectroscopic and some are photometrics. So for the spectroscopic one, we consider the currently available. We have ASIAA, the BOSS and Ebo survey, and also DESI. And in the very near future, we'll also get data from Euclid and Roman Space Telescope. And also, as I mentioned, SPHEREx itself will produce a low-resolution spectroscopic data. Okay. And this spectroscopic data are mostly focused on the low redshift. But for the higher redshift, we can also consider doing this cross-correlation with the upcoming photometry survey, like the Rubin Observatory, LSST, and also the Roman Space Telescope that can even access to the much higher redshift. Right. Okay. So here's our forecast of the sensitivity SNR on the clustering amplitude. So we only focus on the large scales here. Okay. So here I'm showing our model for redshift 1, 2, and 3. And on the top, this is the bias factor times this DIDZ. So this is the EBL as a function of redshift. So this whole quantity is proportional to the amplitude of the clustering power spectrum. Okay. And this is our model of the spectrum we'll see with SPHEREx. So here we have some continuum SED and also some spectral line features here. And this is using the true SPHEREx spectral resolution. Okay. And on the bottom is our forecast of the sensitivity SNR per spectral channels in SPHEREx. Okay. So here we consider this cross-correlation using SPHEREx image with the SPHEREx spectroscopic galaxy catalog showing red, and also the DESI spectroscopic samples. I think this one is out of favor. Okay. Yeah. Okay. So in our forecast, we think we can measure this cross-correlation signal at the SNR above 10 for redshift 1 and 2. And at redshift 3, we only get maybe like 2 or 3 sigma detection here. And this is mostly because at such a high redshift, we don't have too many spectroscopic samples, so we are totally suppressed by the Poisson noise. But we can actually do better if we consider doing this cross-correlation instead using the photometry data, for example, using the data from Rubin LSST. So in this case, we can get a lot more galaxy samples, and we can boost our SNR to about 10. Okay. But the downside of using photometric galaxies is, you have a question?
So there is another remote.
Okay. Right. Okay, so the photometric sample here, the LSST, we think we can get an SNR about 10. But the downside of using it is that because it has a lot more photometric error, so we can only use a wider redshift slice, and that kind of wash out some of the small features in the galaxy SED here. Okay. And with the photometric sample, we can even extend to the higher redshift. So here is our same forecast, but for redshift 4, 5, and 6. And again, on top is our forecast of the bias times the redshift-dependent EBO dIdZ as a function of frequencies. And on the bottom is our forecast of the SNR per spectral channel if we do this cross-correlation with the LSST galaxies. And here at redshift 4 and 5, we can still get the SNR for at the order of 10. And for the higher redshift 6, we can still get some detection here. Okay, so overall, this will be a very promising resource if we can measure this redshift-dependent EBO all the way from redshift 0 to about redshift 6. So it's almost the reionization redshift. So if we have this kind of data, we can do a lot of science with this. So for example, you can try to constrain the history of the star formation or the stellar mass density, and also with the spectrum, and we can even resolve the spectral lines. So with the spectral line, you can also study the evolution of this, the property of the gas across the redshift. Okay. Okay. And
so just use this as the laser pointer and then still kind of control this light.
Okay. Yeah, thank you. Great. Okay. So finally, I also want to mention that remember we have a very high signal to noise on the Poisson noise. So this is like doing stacking on the external tracers. Okay. So we can use this to try to constrain some average property of a certain kind of galaxies when we do these cross correlations. So here's an example. If we do this cross correlation with some quasar samples with some typical quasar spectrum here, then we can detect this average quasar spectrum with a very, very high signal to noise ratio. So this error bars here has been brought up by 1,000 times. Okay, so here's a short summary of the first part of this talk. So here I'm showing you that we can, using this cross-correlation method, to try to extract the redshift-dependent EBO. And according to our forecast with SPHEREx, we can get a pretty high sensitivity measurement on this SPHEREx image and galaxy cross-correlation. And if we can detect this kind of signal, then there will be a lot of interesting science we can do, especially constraining the higher redshift universe. Okay, so is there any question before I move on to the second part?
Yes, what's the orbit of the Spherics?
So what's
the satellite? SPHEREx.
Yeah.
So what's the orbit?
Orbit of Spherics. I think it's like it's orbiting like north-south.
So low Earth orbit.
Yeah.
That's polar.
Right, polar.
And not super low, but not as low as HST, for example.
Right. Okay, so let's look at the second part. So the second project is called the three-dimensional Litho analysis. And this one is in collaboration with Ben Wondell from IAP in Paris, and he's also in CCA, and also Cizhing Zhang and Olivier Doré from JPL and Caltech. And this one is still work in progress, and we are now wrapping up the paper. Okay, so let's first think about how can we describe the signal we see in the data. And here again, the data we consider this kind of multi-frequency imaging data. So we have an intensity map at each frequency channels. So we can describe our data set is an intensity I as a function of angle on the sky, and also some wavelengths here. Okay, so this is the data we can get. And how can we describe the signal in this data we see? So the signal here is basically the integrated emissions from all the galaxies within a light cone of our observing area. Right? So you got the emission from all these galaxies across all redshifts. Okay? And now let's suppose that we can classify these sources into a few different classes of source. So just an example, let's say we only have 3 classes of source in our universe. We have some red ones, blue ones, and green ones. Okay. And then let's assume for each class of source, all the galaxies have exactly the same SED. So for example, I can say, okay, we can classify the emission in our universe from the red, maybe they are the old galaxies, and these galaxies have a very old red spectrum here. And maybe the second type is the star-forming galaxies, and they have some typical spectrums like this. And maybe the third type, the green one, are the quasars. So they also have a much different spectrum here. Okay. And also I want to say, although here in this example, I'm classifying individual galaxies, but this kind of description can be more general. I can do a kind of like the principal component analysis, a PCA, on all the SEDs of the sources in our universe. And with this PCA, you can find out some principal modes. And this principal mode might be, maybe the first mode is some kind of continuum, and maybe some modes are representing, say, the 4,000 angstrom break, for example. Okay. And then we can pick out a few most important principal modes, and then we can only use these modes to approximately describe all the emissions in our universe. Okay. And then for each of these classes, we also need to quantify another quantity called the luminosity density. So this is telling you what's the total luminosity we get per unit co-moving volume as a function of redshift. Okay. So this kind of tells you how many galaxies or how bright the galaxies are for each of these different classes of sources. Okay. And this function should be a very smooth function as a redshift. So for example, you don't expect to see red galaxies only at redshift 1, and they totally disappear at redshift 0, or at redshift 0.9. Okay. So this should be a very smooth function. Okay, so now let's say we can describe our universe in this way. Then let's try to write down the data we see here, I as a function of angle and wavelengths. Okay, so here, this I, now we have to integrate over all the sources across redshift, so we have the integration on Z. Okay. And then within this integration, we sum over the emission from all these different classes. So here I have 3 classes, class 1, 2, and 3. And for each of them, we have some SED, I call it S. And this is kind of a convolution because for a given observed wavelength, I'm sampling the SED at some redshifted wavelengths. And then it is also multiplied by this luminosity density to tell you how much signal you want from each redshift. Okay. And then this whole signal is tracing the underlying matter density field. So here I have a delta M here. And here especially I consider large scales, so they should be a pretty good tracers of the underlying density field. Okay, so now I have a way to describe my signal if I can break down our emissions into these few different classes. Okay, and in cosmology, it's usually easier to look at the signal in the Fourier space. So in the Fourier space, now the matter density field can be simply connect to the matter Paul spectrum here, P of k. And then from this Paul spectrum, we can further connect to some underlying cosmological parameters. Okay. And similarly, I can also do the Fourier transform on my data here. So now, if I do a Fourier transform, then this one becomes I as a function of the spherical harmonics mux L as a function of frequencies. And again, I have the similar term of these S and M from the signal, the SED of the source, and their luminosity density as a function of redshift. And then I get a Fourier transform of the underlying density field here. Okay, and now I want to connect to the Paul spectrum, so I will take the covariance of my data. So when I look at the covariance of the data here, then the covariance here become the angular Paul spectrum, CL. And then I can take this covariance from different frequency slices. So it's a CL as a function of lambda and lambda plumb. Okay. And this data covariance is you take the covariance of this term, so you get something like this. So you have this, the first part is the signal part, describing your SED of the source and the luminosity density, and then you have the Paul spectrum. Okay. And finally, in the real measurements, we not only have a signal, but we always get some kind of noise. So I have another Paul spectrum coming from the noise. And this noise can include all the instrument noise you might have in the measurements, and also all kinds of foregrounds that is not being described by the first term will become the noise. So for example, the noise coming from our own Milky Way, there might be the Milky Way stars or dust, or even like the zodiacal light inside our own solar system. They are all kind of source in the noise. Yeah.
Yeah. So I'm trying to understand what are the assumptions in your big equation there? So it looks like you're assuming. Are you assuming that the mass to light ratio is the same everywhere? It's spatially independent.
The mass to light ratio. I think we don't even need to assume the individual correlation between source and the underlying mass if you consider very, very large scales. So they just basically trace the same kind of partial structure. But yeah, let me think.
So
yeah.
Literally on the equation, you have light on the left hand side, and then you have delta n, which is matter density.
Right.
And you write out linear equation.
Right, exactly.
And then I was wondering at which regime this is valid and large effect, because at large scale, then one might choose to model this using linear galaxy clustering, but there you have the bias factor and so on.
Yeah, exactly. So indeed, I didn't show here, but when we consider different classes, we indeed need to have different bias factor for these different classes. So for example, like in my blue and red galaxy example, you might think that you should have different bias factor for each class. But on very large scales, you can think there are just some kind of linear scaling for all these emissions.
Okay.
Yeah. Okay, so so now this is the main equations of our analysis. So we want to describe our signal, the crossbar spectrum between all different frequency slices in terms of the summation of a few classes of source, tracing some underlying density field, Paul spectrum here, and some noise. Okay, and what we really want to do in the real data is kind of doing this from the other way around. So we measure the data here, intensity as a function of angle and frequencies, and then we'll take the cross-Paul spectrum from all different frequency slices to get this CL as a function of lambda and lambda plumb. Okay, and with all this data, we'll pass these CL measurements into some black box algorithm here to do inference, and then we try to infer the underlying signal, so the SED of different class of source, and the source density, so the luminosity density as function of redshift for each class, and underlying larger structures, which means the larger Paul spectrum, and also the noise inside data. Okay, so that's the whole story of this world. That's what we are trying to do here. Okay, so what is happening in this black box algorithm here? So here we use an algorithm is adapted from the SPHEREx algorithm, and SPHEREx was first developed by the CMB community. They're trying to use this to do the component separation in their CMB data. And SPHEREx is a framework that can simultaneously solve for the signal and noise inside the data. Just look at the data covariance. So data covariance, I mean the CL lambda prong. So all kind of correlation between your data points. Okay. So in this framework, we can simultaneously solve for all this information we want in the data. So here, we want to solve the astrophysics of the source. So we want to know the SED and the luminosity density for different classes of emissions. And also we want to solve for the cosmology part, so the larger structures traced by the matter-power spectrum. And also, at the same time, we also want to infer a lot of nuisance parameters in the data, which is the noise and the foregrounds. That is all the things we need to model in the data. Okay. And we developed this algorithm that we can solve for all this information just from all these CL lambda prong measurements. Okay. Okay. And I want to emphasize that, so this method is quite different from what people usually do with this kind of large-scale cosmological survey. So usually, when people do this larger survey, they first take their image, so they are also measuring like multiple frequencies and some larger images. And the first thing they do is to try to resolve the bright sources in the map. And then for each bright source, then you look at your spectrum. So with the spectrum, with your SED, you can already kind of understand some of the physics of that individual galaxies. And also with the SED, you will do either a photo Z or the spectral Z and fit to some, maybe some SED libraries. And then you can get an estimate of the redshift of the galaxies. So then you can map out a 3D distribution of the galaxies on the sky. And then we can finally do cosmology by this distribution of these galaxies to trace the larger structures. But here, in our framework, we are not trying to resolve any individual sources in the map. We just directly use the full information we get from the raw image. And then we can infer all this information simultaneously without doing this kind of source detection process. Okay. Okay. And I won't go into the detail of how this algorithm works, but just want to give you a sense that, yes, we do have a lot of information from the data that we can solve for all these things we want in our inference. So let's do a very simple dimensional analysis. Okay. So let's think about what's the degree of freedom of the we have in the data. Okay. So here our data is described by this CL lambda prong. So the cross-power spectrum between all different frequencies. So let's say we have n lambda of frequency bands in our measurements. So in total, we'll have an order of n lambda square of this cross-power spectrum, right? Okay. And for each of these cross-power spectrum, we also look at a few different multiple modes. So we have some NL modes, L modes that we can measure. Okay. And let's consider if we do this with SPHEREx, then SPHEREx have about 100 spectral channels. So here, n lambda square is about 10 to the 4. And for the number of L modes, we usually look at maybe like a few tens of L modes in the measurements. So we'll always do some kind of binning. Okay. So in total, we'll have maybe like an order of 10 to the 5 degree of freedom in the data. Okay. And how much information we need to solve for all these things on the right-hand side. Okay. So here I want to solve information in the signal, so this green part, and also we need some information for the pulse spectrum, the larger structure, and also we need some degree of freedom for the noise. Okay. So the number of parameters I need to solve is the sum of the parameters for these 3 different components. Okay. So let's estimate how much information we need for the signal part. Okay. So as I mentioned, we can do maybe kind of the principal component analysis on all the SEDs in our universe to find out a few principal modes of this emission field. So we have some number of classes, and I think this number we can maybe use maybe like an order of 10 or a few tens of the classes of source. That would be very sufficient to describe all these SEDs in our universe. And for each of the class, we need some parameters to quantify their SED and their luminosity density, S and M. So for the SED, I think to describe the full information in the SED, we also need maybe like a few tens of parameters, especially for Spherics or for some, if we think about some kind of photometry data, we don't have the very, very high spectral resolution, so you also don't need a lot of degree of freedom on the SED. And the luminosity density, they are usually a very smooth function of redshift, so I think only a few parameters will be very sufficient. So overall, for the signal, maybe a couple hundreds of parameters will be a very good model to approximate the whole emission fields. Okay. And for the pulse spectrum part here, so if you think, just think about the standard line of CDM model, then we just need 6 cosmological parameters. But of course, you can also add a few more parameters for the cosmology part. So maybe in total you need like 10 to 20 parameters. Okay. And finally, for the noise part, this really depends on what kind of wavelengths and what kind of instrument you have. But the nice thing is that we usually have a very good idea of what the noise, different type of noise will look like. So for example, if you think about the instrument noise and what's the instrument noise in this crossbar spectrum, then maybe in the instrument you should expect like they don't have a lot of correlation between different frequencies because they are totally taken from different kind of electronics, for example, then that reduces a lot of degree of freedoms. And for the foregrounds, for example, like the galactic dust, then maybe they don't have a lot of small scale fluctuations, or they have some kind of power law kind of spectrum. So you can you have some kind of idea to better parameterize your foregrounds. So that also reduces a lot of degree of freedom. And in total, I think maybe at the order of like a couple hundreds of parameters will already be a lot to capture all kind of noise in the data. Okay, so overall, we only need this one plus this one plus this one number of parameters to capture all this information here. So this is at the order of a couple hundreds. Okay, so I hope this can kind of convince you that yes, we do have a lot of information from the measurement that we can try to solve all of this at the same time without having a lot of assumptions like assuming what would be the SED looks like or what would be the noise pulse spectrum looks like. Yeah. Okay, so now I'm going to show you a few example cases and show you the results of running our algorithm here. So here I'm showing you one of our most simple case. So here I assume I only have one source class. So that means all the sources in our universe have the same SED. And the SED looks like this. So we made some typical feature in the galaxy SED, like they have some 4,000 angstrom break here. And this is the 1.6 micron bump. Okay. And the luminosity density, we just assume a very smooth line as a function of redshift. And here we consider the signal coming from redshift 0 to 3. And the underlying raster structure follows the linear pulse spectrum, looks like this. Okay. And then we consider this is a measurement coming from a combination of 9 photometric bands. And we use the photometric wavelengths from the future LSST in optical and 3 near-infrared band in Euclid. So in total, we have 9 bands. So this is kind of the our bands at redshift 0. So at redshift 0, we'll probe the galaxy SED of this part. But when we look at the signal coming from the higher redshift, because the signal is redshifted, so at redshift 3, we can probe the shorter wavelength part of the SED. Okay, so now we have this very ideal case of the universe with all the galaxies have the same SED and this kind of luminosity density and the power spectrum, and with this kind of measurement, and then we can model what's the cross-power spectrum we get, so the CL lambda plot. And then with all this cross-power spectrum, then we can input to our black box algorithm, and then we can try to infer these 3 components inside the data set. Okay, so let's see what we get. Okay, so here's our results. So this is the SED and the luminosity density and the power spectrum, and the black dashed line here is our input model. And the blue color here is the 1 sigma constraint we get. Okay. And on the top is the is a fit to the model, and the bottom is the fractional error from these 3 different quantities. So in this specific example, we can constrain the SED with a very high accuracies. So yeah, the error here is less than 1% for most of the part here, except for the very short wavelengths. And this is because here we don't have a lot of intrinsic signal, and also this can only be probed by the higher redshift sources. Okay. And for the luminosity density, we can also get the right answer with the less than 5% error. And finally, for the power spectrum here, we can get a constraint at the order of about 20% error. Okay. So with this very simple example, we kind of show that yes, we do have the way to extract all this information just from the multi-imaging data. Okay.
Sorry.
Yeah.
This power spectrum is an underlying matter power spectrum.
Right.
How did you break the degeneracy with bias? But I think now, if I understand correctly, bias depends now in MV, not in PK. So how did I thought amplitude totally arbitrary? I thought that the error is too small.
Yeah, that's a good point. So the question is how do we break the degeneracy of the bias in the power spectrum and the luminosity density, right?
Right.
Yeah, so the short answer is you are right, they are totally degenerate. So here I think the best thing we can do is just to fit the shape of the power spectrum. And the bias is, because it's especially at large scales, the bias is just kind of a constant scaling. So that totally degenerate with the luminosity density. So here we can only constrain the shape of the power spectrum. And in this part, we are kind of cheating, so we know what's the answer of the true bias, so we can do the right scaling for this one and this one.
I see.
Yeah, but you're right. Like in reality, we don't know if the true signal is like maybe luminosity density is here and the power spectrum maybe is here. Yeah, this kind of thing we cannot tell.
I think so, but I think in real data analysis, you need to have some feature like BL or something to break the degeneracy. Otherwise, or you get the combination of these two. Right.
So I think in practice you might have some other way to know the bias factor, but if you don't, then they are just totally degenerate. But we can still try to constrain the shape, and just from the shape we can still do some a lot of analysis here.
Right. But
yeah.
If not BL, then you're passing just a power, so not much shape.
So we actually have input some BAO signal here, but it's very small, so it's very hard to tell. Yeah.
So in this exercise, what is the range of K or L that you're using? Is it specifically the linear?
So for the range of K, we use just like showing here, 10 to the minus 2 to about 10. So it's already getting a little bit of nonlinear region here. But also you can see like our best constraint is actually around here. So it's k of 10 to the minus 1. So here it's actually still like in the linear region. Yeah. Okay. And finally, we also run another example. So now it's more interesting. We have two classes. So that means we have two types of galaxies in our universe. So first one have a SED, something like this. And the second one have SED, something like this. And they also have different luminosity density. And they all trace the same underlying pole spectrum. Okay. So in this example, you can see our constraint on SMM, the SED, and luminosity density is worse than the single class case. But we can still kind of capture the right trend here. And the pole spectrum constraint is not degraded a lot compared to SED and luminosity density, because you constrain the pole spectrum with the same pole spectrum or the same larger structure with both type of sources. Okay, so those are just a few preliminary results we get, and we are still looking at a few different cases and trying to optimize our algorithm and to see at which region we can perform better with this algorithm. Okay, so just a short summary of this second part. So we developed this, we call the light cone analysis, to look at the multi-frequency intensity maps. And we try to use it to study the both cosmological and astrophysical information inside this kind of data. And also this is, I can say it's like a very data-driven approach, because we don't need to make a lot of assumptions on the signal and the pole spectrum or the form of the noise in our data. Okay, so here's the last slide of my talk. So here I show you two different projects trying to look at the diffuse extragalactic background light, and we're trying to extract the information, either the cosmological information and astrophysical information, using this diffuse imaging data. Okay, and this will be a very important technique we need for the upcoming large-scale surveys, including the SPHEREx I introduced, and also, you know, in the next couple years, we'll have the Rubin Observatory, LSST, the Euclid, and Roman Space Telescope. So all of these surveys will have this kind of large-scale imaging data that we can start to think about how can we extract the information from this very diffuse background light, not just looking at those individual bright sources like what we did traditionally. Okay, so yeah, I hope this talk can give an idea that there are a lot of interesting things we can try to study in this diffuse EBO background. Okay, yeah, thank you very much.
Could you turn up the microphone so we can go for environment? Are there any questions for Yun-Ting?
Yeah, I just want to make sure I understand the last part. So, so the input data you are assuming is like a multi-wavelengths, just intensity information from the images.
Right.
Okay, so you even like it's unrelated to the first part. You don't need to do like cosmic redshift, etc. You can, I assume that you can directly constrain those information directly from the intensity. The multi-channels, if you use those information, which also include the large-scale information, then simultaneously you can constrain all the things in principle.
Yes, exactly. So we're not trying to use any external information in there.
So the input is just the imaging or the intensity of as a function of wavelengths.
Right.
Okay. And then my second question is, I wonder whether or not you will expect some degeneracy at some point, because currently you are, for example, your example is just two classes of galaxies, but you can imagine there are, I don't know, many types of galaxies, and galaxies evolve, and they show different features at different redshifts. And I'm just wondering whether or not at some point you will get like totally off SED, but I mean the luminosity density also off, and then you will compensate will reproduce the same observed information.
Yes, that's a good question. So yeah, that's totally possible to happen, and that's also why we're thinking that maybe doing kind of the PCA on the SED would be a more robust way for this algorithm than just to classify individual sources, because that kind of capture the most dominant signal that traces the underlying logical structure. But of course, like as you mentioned, like the galaxy's physics is very complicated, so we always have to be very careful and trying to test different cases to see if our algorithm will break down in some scenarios.
Roger, do you have a question? Okay. Are there any other questions for Yun-Ting? Could you go back to the first, at the end of the first part where you showed the shock noise constraint, I guess, for quasars? Yes, this one, right? I always kind of expected the error bars to blow up at 3.7 micron above, where spectral resolution get higher, but then the depths of the photometry gets worse.
Yeah, I think it will get worse a little bit, but I don't think it's a very obvious. Yeah, I have to check, but I remember that the sensitivity drop is not very obvious for this case.
Okay. Okay. We'll check with you afterward. Yeah. Are there any other questions for Yun-Ting? Okay. If not, Yun-Ting will still be here for a few more hours.
Yeah.
Right, and then she had a few meetings scheduled already, but I believe there are also empty slots, so feel free to chat with her while she's here. And thanks Yun-Ting again.